Section: Introduction. In this section, we will discuss the key points from the introduction. We start by mentioning the OpenAI scaling law paper from 2020, which compared LSTMs to transformers and highlighted the limitations of LSTMs in handling long contexts effectively. We now revisit these findings using modern RNNs and best practices. In the figure presented, we see that Mamba, a popular RNN today, has made significant progress compared to LSTMs in 2020 and scales similarly to a strong transformer. However, similar to LSTMs, Mamba also faces challenges with long contexts. Transformers outperform RNNs like Mamba in predicting tokens later in a sequence because they can leverage more information as the sequence progresses. This advantage is evident in transformers as their average perplexity decreases throughout a 32K context, whereas Mamba's performance plateaus after 16K. The struggle with long contexts is inherent in RNN layers because they need to compress vast amounts of context into a fixed-size hidden state. Unlike self-attention mechanisms in transformers, RNN layers face difficulties in capturing the complex relationships among thousands or even millions of tokens efficiently. Building on the idea that self-supervised learning can compress vast training data into model weights, we introduce a new class of sequence modeling layers called test-time training (TTT) layers. In TTT layers, the hidden state is a model, and the update rule involves a step of self-supervised learning. We propose two simple versions within this class, TTT linear and TTT MLP, where the hidden state is a linear model and a two-layer MLP, respectively. These TTT layers can be seamlessly integrated into various network architectures and trained end-to-end. To enhance the efficiency of TTT layers in terms of wall clock time, we introduce two practical innovations. Firstly, we adopt mini-batches of tokens during TTT, similar to gradient steps on mini-batches during regular training. Secondly, we develop a dual form for operations within each TTT mini-batch, enabling faster training on modern GPUs and TPUs. In our evaluations, TTT linear demonstrates superior performance compared to transformers and Mamba across different parameter ranges. We also highlight open problems and encourage the research community to collaborate in finding solutions. Our contributions include proposing TTT layers as a novel approach to sequence modeling, showcasing the efficiency of TTT linear, and improving hardware efficiency through mini-batch TTT and the dual form. We then delve into the methodological aspects, emphasizing the importance of effectively compressing historic context into hidden states for efficient and expressive sequence modeling. RNN layers compress context into fixed-size states, while self-attention mechanisms maintain a growing list of key-value pairs for each token. Balancing efficiency and expressiveness in handling long contexts requires innovative compression heuristics, which is a key focus of our work. Section Summary. In this section, we explore the limitations of existing RNNs, like Mamba, in effectively utilizing long context for sequence modeling. While RNNs have linear complexity advantages over transformers, they struggle to leverage the extra information from longer contexts due to the inherent compression limitations of RNN layers. To address this, we introduce test-time training (TTT) layers, a new class of sequence modeling layers where the hidden state is a model updated through self-supervised learning, offering improved efficiency and performance compared to traditional RNNs and transformers. Section: TTT as updating a hidden state. In this section, we view the process of parametric learning as compressing a large training set into a model's weights. Models trained with self-supervision can capture the underlying structures and relationships in the data they are trained on, which is crucial for compression. Large language models, LLMs, are prime examples of this. They are trained to predict the next token in a self-supervised manner, and their weights store a compressed form of internet knowledge. By querying LLMs, we can extract knowledge from their weights, as they understand the connections among pieces of information to generate new reasoning. Our main idea is to use self-supervised learning to compress historical context into a hidden state by treating the context as unlabeled data and the state as a model. The hidden state is represented by the weights of a model, which can be a linear model or a small neural network. The output is determined by applying the model to the current input. The weights are updated using gradient descent based on a self-supervised loss function. From a compression perspective, the model decides which inputs to remember based on the gradients they produce. One approach is to reconstruct the input itself by processing it into a corrupted form and then optimizing the difference between the model's reconstruction and the original input. This process requires the model to understand the relationships between different dimensions of the input to reconstruct it accurately. Our algorithm maps an input sequence to an output sequence using the hidden state, update rule, and output rule. This can be integrated into a sequence modeling layer for both training and testing. We introduce the test time training (TTT) layer, which trains a different set of weights for each input sequence even during testing. The TTT layer can be seamlessly integrated into larger network architectures and trained similarly to other language models. The training process involves optimizing the parameters of the network in two nested loops. The inner loop optimizes the weights within each TTT layer, while the outer loop optimizes the rest of the network parameters. We explore ways to enhance the TTT layer's self-supervised task and improve its efficiency in subsequent subsections. Section Summary. In this section, we explore the concept of updating a hidden state, denoted as TTT, by compressing historical context into model weights through self-supervised learning. By utilizing self-supervised tasks like next token prediction, large language models, LLMs, can store existing knowledge in their weights, enabling extraction of knowledge and expression of new reasoning. The TTT layer, integrated into sequence modeling, allows for training different weights for each input sequence, functioning as a test time training layer with inner loop gradients optimized separately from the outer loop parameters of the network. Section: Learning a self-supervised task for TTT. In this section, we focus on learning a self-supervised task for TTT. The self-supervised task is crucial in determining the features that our model will learn from the test sequence. Instead of manually crafting a self-supervised task based on human knowledge, we take a more direct approach by optimizing the task for the ultimate goal of next token prediction. To make the self-supervised task learnable, we incorporate it into the outer loop. We start with a basic reconstruction task and enhance it by introducing outer loop parameters to facilitate learning. One way to generate the corrupted input, $x_t from x_t, is by using a low-rank projection, where $x_t equals theta_k x_t, with theta_k being a matrix that can be learned. This transformed input, theta_k x_t, is referred to as the training view. Additionally, to focus on essential information in x_t, we can use another low-rank projection as the reconstruction label, denoted as theta_v x_t, where theta_v is also a learnable matrix. The new self-supervised loss function is then defined based on the difference between the transformed input and the label view. It is important to note the distinction between the optimization of W and the various theta parameters. In the inner loop, only W is optimized, while the theta parameters act as hyperparameters of the loss function. On the other hand, in the outer loop, theta_k, theta_v, and theta_q are optimized together with other parameters, and W serves as a hidden state rather than a direct parameter. By introducing a test view theta_q x_t, we enhance the flexibility of the self-supervised task. This test view allows for different information from x_t to be mapped to the current output token z_t, providing more versatility in the learning process. The choices of theta_k, theta_q, and theta_v lead to a range of multi-view reconstruction tasks, and the outer loop essentially selects a specific task from this set. Furthermore, we discuss the parallelization of TTT with mini-batch processing. While the basic TTT layer is already efficient in terms of operations, the update rule cannot be parallelized due to dependencies on previous time steps. To address this, we propose mini-batch gradient descent, where gradients are computed in batches to improve efficiency without compromising performance. The choice of batch size B influences the trade-off between speed and quality in training. In our experiments, we set B equals 16 to balance these factors effectively. Section Summary. In this section, we focus on learning a self-supervised task for TTT, which is crucial for determining the features that W will learn from the test sequence. Instead of handcrafting the self-supervised task based on human priors, we take an end-to-end approach by directly optimizing it for the final goal of next token prediction. We introduce a new self-supervised loss function that includes learnable parameters theta_k and theta_v, enhancing the flexibility and performance of the task. Section: Dual Form. In this section, we introduced parallelization to improve efficiency in wall clock time. Modern accelerators like the NVIDIA A100 GPU excel at matrix-matrix multiplications, known as matmuls. These GPUs have specialized units called tensor cores optimized for multiplying two matrices of size 16 times 16. However, if there are not enough matmuls to keep the tensor cores busy, the full potential of the A100 GPU remains untapped. Our current TTT layer, even with mini-batch processing, lacks sufficient matmuls. Let's consider a simple scenario where theta_k equals theta_v equals theta_q equals I for the first TTT mini-batch of size B, and F is a linear model. The loss at time t can be represented as the square of the difference between W_0 x_t and x_t. We can parallelize the computation of G_t equals nabla L W_0 x_t for t equals 1, L dots, B. However, we cannot compute all G_t through a single matmul. Instead, we need B outer products to calculate them individually. This leads to heavier memory usage and I/O costs for each G_t compared to x_t when D is large. To address these issues, we realize that we don't need to compute and store all G_t values explicitly. Instead, we can compute W_b at the end of the mini-batch and the output token Z_1, L dots, Z_b without explicitly calculating G_t values. By simplifying the TTT linear case, we can compute W_b conveniently using a matmul operation. Similarly, we can compute Z equals Z_1, L dots, Z_b, by utilizing W_b and a term called delta, which can also be computed efficiently with matmuls. This approach, known as the dual form, contrasts with the primal form where G and W values are explicitly computed. Both forms yield equivalent results. The dual form sacrifices theoretical complexity for better hardware utilization. In practice, with typical values of D and B, the dual form significantly reduces the time taken to compute Z_1, L dots, Z_b compared to the primal form. In our JAX implementation, training with the dual form is more than 5 times faster than with the primal form. Section Summary. In this section, we discuss the necessity of parallelization for efficiency in wall clock time, particularly focusing on matrix-matrix multiplications, matmuls, on accelerators like the NVIDIA A100 GPU. We introduce a dual form approach that optimizes hardware utilization by computing W_b and output token Z_1, dots, Z_b without explicitly materializing all intermediate computations, resulting in faster training compared to the primal form. Section: Theoretical Equivalences. In this section, we mentioned that our function f can either be a linear model or a neural network. We also discussed 3 different versions of the update rule: online gradient descent, GD, batch GD, and mini-batch GD. Each combination of these two factors leads to a different setup of the TTT layer. We found that the TTT layer with a linear model and batch GD is essentially the same as linear attention, which is a well-known recurrent neural network, RNN, layer. Let's consider the TTT layer with f(x) equals wx as the inner loop model, batch GD with a specific update rule, and starting with w_0 equals 0. When we apply this setup to the same input sequence x_1, L dots, x_t, the output sequence z_1, L dots, z_t generated matches that of linear attention. We verified this equivalence empirically in a table by enhancing the implementation of linear attention. By gradually adding components to the TTT layer equivalent to linear attention, including some upcoming ones, we created a new instantiation called TTT linear. The switch from batch GD to mini-batch GD showed the most significant improvement. While the combination of models and optimizers in machine learning is vast, it's not limited to just optimizing parameters like w_t in a model F. There are also non-parametric learners like nearest neighbors, support vector machines, SVMs, and kernel ridge regression. These learners do not have parameters like w_t but directly use training data x_1, L dots, x_t. We demonstrated that for a specific non-parametric learner, the induced TTT layer is equivalent to self-attention. To bridge the gap between parametric and non-parametric learners in the TTT layer framework, we introduced a new concept called a learner. This learner uniquely defines a TTT layer by implementing two methods, train and predict. This approach allows us to include both parametric and non-parametric learners in the TTT layer framework. Additionally, this new definition enables the use of more advanced optimizers like ADAM in future research. Section Summary. In this section, we explore theoretical equivalences between different instantiations of the TTT layer, considering variations in models like linear or neural networks and update rules like online GD, batch GD, and mini-batch GD. We demonstrate that a TTT layer with a linear model and batch GD is equivalent to linear attention, a well-known RNN layer. By introducing a new abstraction called a learner, we show that both parametric and non-parametric learners can be included in the TTT layer framework, allowing for a broader scope of sequence modeling layers and potential use of advanced optimizers like ADAM. Section: Implementation Details. In this section, we introduce two variations of TTT layers, TTT linear and TTT MLP. These variants differ in how the function f is defined. In TTT linear, f is a linear function denoted as f_text lin x equals wx, where w is a square matrix. On the other hand, in TTT MLP, f consists of two layers similar to the MLPs in transformers. The hidden dimension is 4 times the input dimension, followed by a JELU activation function. To enhance stability during TTT, the function f always includes layer normalization, lane, and a residual connection. This means that f(x) equals x plus text lane f_text res x, where f_text res can be either f_text lin or f_text MLP. We also explore the inner loop learning rate eta in our experiments. We make eta dependent on the input token, allowing it to vary over time for added flexibility. Specifically, we define eta x equals eta_text base CDOT sigma theta_text LR CDOTx, where eta_text base is the base learning rate, set to 1 for TTT linear and 0.1 for TTT MLP. Here, theta_text LR is a learnable vector, sigma is the sigmoid function, and eta x can also be seen as a gate for nabla L. When integrating any RNN layer into a larger architecture, replacing self-attention in a transformer with a backbone is a straightforward approach. We find that incorporating the Mamba backbone, which includes temporal convolutions before the RNN layers, improves perplexity for TTT layers. Therefore, we adopt the Mamba backbone in our proposed method. To evaluate the performance of TTT linear and TTT MLP, we compare them with two baseline models, Transformer and Mamba. Our experiments are conducted using EasyLM, an open-source project for training and serving LLMs in JAX. All the code and datasets used in our experiments are publicly available for reproducibility. In our experiments, we use datasets with context lengths of 2K and 8K from the PILE dataset. Additionally, we experiment with context lengths ranging from 1K to 32K in increments of 2x using a subset of the PILE known as Books 3, which is commonly used for training LLMs with long contexts. When discussing backbone architectures, we note that TTT linear and TTT MLP typically utilize the Mamba backbone unless stated otherwise. As part of an ablation study, we incorporate TTT layers within the Transformer backbone, denoted as T, and the Mamba backbone, denoted as M, in our figures. To ensure fair comparisons with our baselines, we adhere to the evaluation protocols outlined in the Mamba paper. This includes experimenting with different model sizes, 125M, 350M, 760M, and 1.3B parameters, and following the chinchilla recipe for training models. Our transformer baseline, based on the Llama architecture, aligns with the Mamba paper's baseline and can reproduce the reported results. We do not explore hybrid architectures like Griffin, as our baselines do not incorporate hybrid models, which could potentially impact the clarity of our evaluation. Section Summary. In this section, we propose two variants of TTT layers, TTT linear and TTT MLP, with different instantiations of the function f. The learning rate for gradient descent is experimented with as part of the outer loop, where it becomes a function of the input token for added flexibility. Additionally, we integrate the Mamba backbone architecture into our proposed method, which improves perplexity for TTT layers. Section. Short context. The PILE. In this section, we made several observations based on the figures provided. At a context of 2K, we noticed that TTT linear, M, Mamba, and Transformer showed similar performance, with TTT MLP, M, slightly underperforming when considering large flop budgets. Despite TTT MLP having better perplexity than TTT linear at each model size, the extra flop cost negated this advantage. Moving to an 8K context, both TTT linear, M, and TTT MLP, M, outperformed Mamba significantly, unlike the scenario at 2K. Even TTT MLP, T, with the Transformer backbone performed slightly better than Mamba around 1.3B. A consistent trend we observed was that as the context length increased, the superiority of TTT layers over Mamba became more pronounced. When we switched the TTT layers from the Mamba backbone to the Transformer backbone, two effects were noted. Firstly, TTT layers with the Mamba backbone generally performed better in our evaluations. Secondly, with the Mamba backbone, TTT MLP was only comparable to TTT linear at best, but with the Transformer backbone, TTT MLP clearly outperformed. We speculated that the temporal convolutions in the Mamba backbone were more beneficial when the sequence modeling layer had a less expressive hidden state. The linear model, being less expressive than the MLP, derived more benefit from these convolutions. Regarding the lack of a linear fit, previous studies observed that optimal models based on computation typically fell on a line in the log-log plot of flops versus perplexity. However, in our experiments, including those in books, we did not find a clean linear fit, even for transformers. This discrepancy was expected due to variations in dataset, context length, tokenizer, and architecture. In our evaluation on long context using the Books 3 subset, we experimented with context lengths ranging from 1K to 32K. Notably, at 2K context on books, similar observations to those at 2K on pile were made, except that Mamba now slightly outperformed TTT linear. At 32K context, both TTT linear M and TTT MLP M performed better than Mamba, akin to the results at 8K on pile. Even TTT MLP T with the transformer backbone showed slight superiority over Mamba at 32K context. The lack of a clean linear fit made it challenging to derive an empirical scaling law, but the trend for TTT-MLP T hinted that the transformer backbone might be more suitable for larger models and longer contexts beyond our evaluations. In practice, while we primarily train transformers from scratch following the Mamba paper, it is more common to fine-tune transformers in long contexts rather than training them from scratch. To reflect this practice, we introduced another baseline, TF fine-tune, for context lengths of 4K and above. This baseline involved starting from a model trained on books 2K and fine-tuning with additional tokens at the designated context length. Our complete results for various context lengths, including TF fine-tune, are detailed in the appendix. We also discussed the context length as a hyperparameter, emphasizing that it is a design choice for engineers. For LLMs with linear complexity, we selected the context length that minimized perplexity, as all context lengths have the same flops. For transformers, longer contexts incurred higher flops, leading us to form a convex hull of all points in the log-log plot and connect those on the boundary. Notably, the best performing methods, TTT linear and TTT MLP, showed highly overlapping lines. TF fine-tune demonstrated significant improvement over TF pre-train, benefiting from long context without excessively high training flops. It is important to note that while TF fine-tune and pre-train had similar inference flops, their performance differed. Additionally, all methods trained from scratch experienced worsened perplexity as context length increased too much. This trend is further elaborated in the appendix. Section Summary. In this section, we observe that as context length increases, the advantage of TTT layers over Mamba becomes more pronounced. When comparing TTT layers with Mamba backbone to those with transformer backbone, we find that TTT-MLP performs better with the transformer backbone due to its more expressive hidden state. Additionally, we note that while linear fits are common in scaling law experiments, we do not observe a clean linear fit in our experiments, especially for transformers, likely due to differences in dataset, context length, tokenizer, and architecture. Section: Wall clock time. In this section, we break down the training and inference process of large language models, LLMs, into three main components: forward, backward, and generate. During inference, prompt processing, also known as prefill, is similar to the forward operation during training, but without the need to store intermediate activations for backward processing. Both forward and backward operations can be done in parallel, so we use the dual form. On the other hand, generating new tokens, or decoding, is inherently sequential, so we use the primal form for this step. Due to limited resources, our experiments are conducted using JAX on TPUs. When comparing the performance of different models, we found that TTT linear is 10% faster than the transformer baseline without any system optimizations. However, the Mamba model, which is implemented in PyTorch, Triton, and CUDA, can only run on GPUs. To ensure a fair comparison, we optimized our method to run on GPUs by developing a GPU kernel for the forward operation in Thunder Kittens. Traditionally, recurrent neural networks, RNNs, have been inefficient due to poor parallelism and matrix multiplications during forward and backward operations. Our goal with the forward kernel is to showcase the effectiveness of mini-batch TTT and the dual form for addressing these inefficiencies. While we have developed a kernel for the forward operation, creating a similar kernel for the backward operation is more complex and is left for future work. In our experiments, we observed that the time per token increases linearly for the transformer model as the context length grows, whereas it remains relatively constant for other methods. Our transformer baseline outperforms the Mamba model in terms of speed, mainly because we use VLLM, a cutting-edge serving system, instead of the hugging face transformer. We also developed a GPU kernel for the generate operation in Triton and evaluated its speed. The throughput metric, which considers the advantage of using larger batch sizes, is also reported in our analysis. The observations and comparisons between different methods hold true for throughput as well. Mamba belongs to the category of structured state space models, where the hidden state is a vector similar to LSTMs. In contrast, models like TTT linear and TTT MLP have larger hidden states represented by matrices. Our experiments show that TTT MLP outperforms TTT linear, which in turn outperforms Mamba in compressing information from long contexts. Modern RNNs like gated linear attention, GLA, leverage matrix hidden states inherited from linear attention mechanisms. These models use chunk-wise parallelism to enhance hardware efficiency, processing tokens within a chunk using matrix multiplications. Mini-batch TTT allows for more complex temporal dependencies across mini-batches, offering a trade-off between model expressiveness and hardware efficiency. Learning at test time has been a concept explored in machine learning for a long time. It involves adapting the model during the testing phase based on the test data. This approach has been successfully applied to various models, including LLMs. Transductive learning is another form of learning at test time, where constraints from test data are used to refine the model's predictions. In computer vision and natural language processing, learning at test time has been instrumental in tasks like face detection, object detection, and dynamic evaluation in NLP. Section Summary. In this section, we break down the training and inference processes of LLM into forward, backward, and generate steps, with a focus on parallelization and efficiency. We introduce a GPU kernel for the forward pass to showcase the benefits of mini-batch TTT and the dual form. Additionally, we explore the concept of learning at test time, discussing historical approaches like local learning and transductive learning, and their applications in various machine learning models, including modern LLMs. Section: Test Time Training. In this section, we explore the concepts of test time training, TTT, fast weights, and learning to learn. The core idea behind TTT is that each test instance presents its own unique learning problem, focusing on generalizing to that specific instance. Typically, in machine learning, we predict the outcome for a test instance using a model optimized for all training instances. However, TTT takes a different approach by formulating a learning problem specific to each test instance and training a model tailored to that instance. This self-supervised learning task, such as reconstruction, has been shown to enhance performance, especially for outliers and sequential data like video frames. Our approach differs from previous methods as we learn the reconstruction task in an outer loop rather than relying on predefined human assumptions. Fast weights, on the other hand, involve updating a fast model's parameters based on the most relevant data, contrary to the traditional method of updating a slow model with all data. TTT can be seen as a special case of fast weights, where the focus is on optimizing the learning problem for the test instance. By explicitly formulating this learning problem, TTT stands out from previous fast weights approaches. The idea of fast weight programmers, FWPs, involves updating fast weights using a slow model, with inner loop weights considered fast and outer loop weights as slow. Networks with TTT layers can be viewed as a specific type of FWPs, showcasing the versatility of this concept in various network architectures. Furthermore, learning to learn, also known as meta-learning, has been recognized as a crucial aspect of intelligence. While previous approaches focused on learning from entire datasets in the inner loop, TTT treats each sequence as a dataset, simplifying the outer loop and making scalability more feasible. By redefining the supervised learning problem as learning at test time, we introduce a new framework for network architectures, offering a vast space for exploration and innovation. Our work represents a step towards leveraging regular training heuristics for test time training, paving the way for efficient search and promising future directions in the field. Section Summary. In this section, we introduce the concept of test time training, TTT, where each test instance defines its own learning problem, and a model is trained specifically for that instance. TTT formulates a learning problem based on the test instance, often using self-supervised tasks, and has shown improved performance, especially on outliers and video frames. Additionally, we discuss the idea of fast waits, which update model parameters based on relevant data, with TTT being a special case of this approach. Section: Author Contributions. In this section, we began this project in November 2022 and have been working on it full-time since then. We developed the conceptual framework, designed mini-batch TTT and the dual form, wrote the paper with assistance, and oversaw the team's daily operations. Our team members have made significant contributions to the project. Shinao Li and Karen Dalal co-led the development of the current codebase. Shinao was instrumental in shaping earlier codebases before March 2024 and provided valuable input on project direction. Karen managed experiments, contributed to writing the paper, and participated in project discussions. Jirui Shu led architectural development and contributed to project direction discussions. Arjun Vikram focused on systems optimization, while Gengan Zhang provided insights for systems optimization. Yann Dubois proposed the current instantiation of a specific function and contributed to project discussions. Zhenlei Chen and Xiaolong Wang have been supporting the project since November 2022, offering guidance on test time training. Sanmi Koijo, Tatsunori Hashimoto, and Carlos Gestrin have also provided valuable advice and support since May 2023. We are grateful for the support from various funding sources and individuals who have contributed to the success of this project.